all. Okay, so the first talk is by Michaela
yes.
and it's like Holger, and it's on a modest approach to the dynamic heuristic search in probabilistic model checking. So can you start playing, please?
Yes, I can start playing. Just a note to all the speakers, this will be recorded and published on YouTube. So if you have any problems, please send me a message if you oppose the recording and publishing of this on YouTube. Yes, and I will start with the first video.
Thank you.
Hi, my name is Michaela Klauk and I will present you the paper A Modest Approach to Dynamic Heuristic Search in Probabilistic Model Checking. The paper is joint work with Holger Hermanns. We already have a set of well-established probabilistic model checkers in our community, like Storm, the Modest toolset, Prism and others. So the question is, why is it even necessary to explore yet another approach to solve problems we already have quite good tool support for? Well, the classical approaches to solve our problems often suffer from the state space explosion problem. For larger models, this is also sometimes the case for symbolic or hybrid methods. Thus, large or complicated models are not solvable in a reasonable amount of time anymore. That's why we explore another approach inspired by the planning community based on dynamic heuristic search in our work. We concentrate on the standard or base model type, Markov decision processes, MDPs for short. Here we see one with a probabilistic action A and non-determinism between A and B. MDPs often reflect concurrency phenomena, and we solve a large set of property types. This includes maximal and minimal reachability probabilities. This means, for example, the maximal probability of eventually reaching a goal state or the minimal probability that x is always smaller or equal to 5 until y equals 3. Similar questions can be asked for maximal and minimal expected accumulated rewards. We also allow that these property types include step or reward bounds, like here for the minimal expected accumulated reward until reaching the goal in at most 20 steps. But MDPs are not only popular in the model checking and concurrency community. They have a longer tradition in the context of sequential decision making under uncertainty with a focus on goal reachability. Heuristics are used to avoid the state space explosion problem. It is tried to compute the optimal value for a state based on only a small fraction of the state space, just sufficient to answer the considered property. So we zoom into the state space. State-wise estimates of the optimal values for only a subset of the state space are exploited. In our setting, we use a procedure called labeled real-time dynamic programming. It is a heuristic search dynamic programming optimization based on a synchronous value iteration. Similar to the basic value iteration, a value is assigned to each state S by a value function specifying the current approximation of the state's value. The value function, called Bellman equation, is placed in an iterative procedure, updating the state's values depending on the values of their successors as prime. Such a function exists for each visited state. The values are refined until convergence to the least fixed point. Often this fixed point corresponds to the optimal value one is looking for. But the difference between original and asynchronous value iteration is that the order in which values are updated is made dependent on their current value estimates. This means finding the optimal values by continually updating the current best solution is done on single exploration path. Only one state's value is updated at each step. The procedure works in a greedy fashion. For exploration, always the action is picked which leads to a successor state with the best value with respect to the current value function. This attempts to avoid exploring the entire state space and delivers the requested value only for the initial state on which the procedure is called. Let's do a quick example together to see and get a better idea on how the procedure works. Here we have a small MDP and we want to calculate the maximal goal reachability probability. The goal state is marked in green. The other state, which is reachable with a probability of 40%, is a dead end. All other actions are deterministic. we call LRTDP on the initial state and initialize it with 1. Then we have to explore it further. There's only one choice to go to the next state, which is also initialized with 1. And the same for the third state. In the end, the dead end has a goal probability of 0, and the goal obviously has a goal probability of 1. Now these values are propagated back, and the Bellman equation is applied. So the value of the predecessor is 0.4 times 0 plus 0.6 times 1. This value is propagated back to the initial state, which in the end contains the maximal goal probability. Unfortunately, this simple LRTDP approach only works on specific MDP structures. For others, which for example contain cycles, LRTDP has to be wrapped in a procedure called find, revise, eliminate traps to guarantee convergence to the optimal value. Special MDP structures which have to be eliminated are first permanent traps, which are bottom strongly connected components without goal states in the underlying graph structure of the MDP. This graph is obtained from the MDP by replacing all probabilistic choices by non-deterministic ones. A strongly connected component is a set of states in which all states are reachable via a path from each other. In a bottom strongly connected component, only states in this set are reachable. Second, transient traps have to be eliminated. These are BSSCs without goal states of the greedy graph, which is constructed by following the actions selected greedily during the exploration in LRTDP, but only SSCs of the underlying graph structure of the MDP. To have an example for this case, we add this loop back to the initial state to the MDP. This means we have a non-deterministic choice here. LRTDP starts as before until the second state is initialized. Now we have two outgoing actions, and the one leading to the successor with the best value with respect to the property we want to solve has to be chosen. We do not know the value of this state here yet. This means before we can decide, we have to initialize it. But this does not help in deciding which action to pick, so we just take one of them and in this case choose the one going back to the initial state. Now LRTDP is done because this state has already been explored. The maximum goal probability of the initial state would be 1, which is wrong. Therefore, Fred enters the game and searches for bottom strongly connected components in the current greedy graph with respect to the value estimates, which is the red part here. And it detects the red cycle, which has to be eliminated to guarantee convergence to the optimal value. This is a transient trap because it's only a strongly connected component of the whole graph, but a bottom strongly connected component in the greedy graph. Now, LRTDP starts from new and walks down this chain similar to what we have seen before, terminating with the correct result. We extended Fred LRTDP to also solve minimal expected reward properties. Here again we have to take care of cycles. The values on the edges are rewards gained when taking the transitions. We start to initialize the state's values, this time with 0 because we want to calculate the minimum, and initial values always have to be optimistic with respect to the property to be solved. The next state also gets a 0. At this point we only go forward through the graph. Updating the predecessor's values with respect to the reward accumulated when taking the actions is done later during the backpropagation step. The third state also gets initialized with 0. Then we have a non-deterministic choice again. And to check which option is the best, we need to initialize the goal state. The reward gained by taking this transition would lead to an expected reward of 1 here. Taking this edge would lead to an expected reward of 0 for this state. Because we want to minimize, we take this option and go back. This would lock us in this cycle forever, therefore it has to be eliminated to make sure that the goal is reached and the correct result is calculated. So we eliminate this cycle, and now the correct value can be propagated back from the goal to the initial state. We propagate back the reward of 1 here and go one step further and go to the initial state. Now we end with a minimal expected reward to reach the goal of 2. A similar example also demonstrates a special case for the calculation of the maximal expected reward to reach the goal. In this case, the maximal expected reward to reach the goal is infinity, because it is possible to always take this loop here and accumulate an infinite reward. Again, we have to take an optimistic over-approximation for the initial value with respect to the property type we want to solve. For maximal expected rewards, this is infinity. As you have seen before, LRTDP walks down the graph and initializes unvisited states. At this point here, we would have to decide which option is the best for the problem we want to solve. It even does not matter what the value coming back from this goal state would be. It is enough to recognize that this edge is going back and closes a strongly connected component. This directly leads to the result of infinity for the whole graph. Because calculating with infinity as an initial value and approaching the actual value from above takes too long in implementations, we found a procedure to iteratively approximate an initial value which fits better. For details, please have a look into the paper. With these examples, I gave you some hints that the combination of red LRTDP can be adapted to solve more property types than just maximal reachability probabilities as in the original works on general MDP structures. This means without limitations to specific reward structures. We had to make a lot of modifications, adaptations and extensions to the original algorithms. They are all listed in detail in the paper. The tool called Modish, implementing all of this, is part of the Modest toolset. It can be seen as an alternative to the explicit state model checking engine and CSTA of Modest. Modish even extends the toolset by supporting property types not supported thus far. For example, step-bounded properties and others. Integrating Modish into the Modest toolset brings the benefit that it supports the same input languages, which are the Modest language and Jani. The current version is available online at modestchecker.net. Windows, Linux and Mac versions are available. To show that Modish, with its dynamic heuristic search approach, is competitive with the state-of-the-art model checkers like Prism, Storm and other engines in the Modest toolset, we run a very large comparative study on models on the quantitative verification benchmark set. The QVBS is a large benchmark collection of probabilistic models, including CTMC, DTMC, MA, MDP and PTA models. For all of the models, properties and evaluation results are available to make comparisons between tools easier. These benchmarks stem from different fields, not only the core classical model checking area, but also from planning domains or fault trees. The benchmarks are available at qcomp.org. qcomp is also the name of the comparison of tools for the analysis of quantitative formal models competition, which is based on the QVBS. Former prototypical preliminary versions of our tool Modish already took part in this competition in 2019 and 2020. That's why we decided to update the results from QComp by running the same benchmarks on the newest version of all tools able to solve MDPs which participated in 2019 and or 2020. In addition, to show the capabilities of Modish, we added more benchmarks from the QVBS and even larger instances. In total, we compared 6 other model checkers and 1 planning tool which implements the original version of Red LRTDP to Modish. This stacked bar chart shows how much benchmark instances of which type are supported by which tool. A tool supports a benchmark instance if it would in principle be able to solve the property on this benchmark independent of time or memory outs. The upper bars visualize the benchmark set originally used in QComp. The lower bars belong to our additional benchmark set. The QComp MDP benchmark set consists of 36 instances, and we added 58 additional benchmark instances to enlarge, for example, the number of minimum reach and bounded properties, and to have extremely large benchmarks with respect to the state space size. Together with Storm, Modish is the only tool supporting all benchmark instances. compared to the planning tool Probabilistic Fast Downward, which implements the original version of thread-LRTGP, it is obvious that we clearly extended the functionality of the procedure. When comparing to MCSTA of the Modest toolset, it is again visible that the support of property types has been extended. The strengths of Modish are clearly visible in the quantile plots, divided into a plot for the original QComp benchmark set on the left, which is directly comparable to the plots in the competition reports of the last 2 years, and the plot for the additional benchmark set. A point xy indicates that the runtime of the X fastest problem instance on this tool was y seconds. This allows comparing the overall performance of the tools. The benchmark instances are ordered independently for each tool, depending on its runtime. The count of correctly solved benchmarks, which means that no timeout or error occurred, and of in general supported instances is given in the label. Modish improved the runtime for many of the QComp instances in comparison to 2020, such that it is now among the best 3 tools for a large amount of benchmark instances. The strength of Modish is impressively demonstrated by the results on the additional benchmark set on the right. It clearly outperforms the other tools on extremely large scale benchmarks because only a small fraction of the state space needs to be visited. Modish is able to solve 7 benchmarks in less than 30 seconds, for which all other tools time out or do not have enough memory. For 5 other models, only 1 other tool is able to solve them. For the largest instances of Dynamic Philosophers, Pneumozook, Rabin and the wireless LAN model, only a few thousand states have to be visited in Modish, where the entire state spaces have 10 to the 100 and 10 to the 8 states for the latter respectively. For Israeli Jelfen, only 10 to the 3 instead of 2 to the 100, which is 10 to the 30 states have to be visited. All these benchmarks have in common that they consist of the parallelization of automata of symmetric structure. The results on both benchmark sets show that Modish is clearly able to compete with the state-of-the-art model checkers, and on certain MDP structures it is even able to quickly solve instances which no other tool is able to handle. More detailed results can be inspected in these scatter plots comparing individual benchmark instances between 2 tools or a tool and the best of all other tools. A point xy indicates a runtime of x seconds for the tool on the x-axis and a runtime of y seconds for the tool on the y-axis. This means if the point lies above the diagonal line, the tool on the x-axis was the fastest. If the point lies above the dotted line, it was even more than 10 times faster. NA means that the tool is unable to handle the benchmark instance. The number of benchmark instances on which the tool on the x-axis outperformed the tools on the y-axis is given in parentheses in the label. By the evaluation setup, the left plot is a direct update of the last QComp results. We see that Modish is able to compete with the other tools, especially on the additional benchmarks shown on the right. It solves way more instances and property types than Probabilistic Fast Downward, which can be seen here, which is based on the same algorithms. And the performance is also quite good. It also shows better performances on many instances in comparison to MCSTA, especially where MCSTA is not able to deliver results at all. This demonstrates the potential of the methods implemented in Modish because first it improves the model checking performance of the Modest toolset in comparison to MCSTA on the same code base. Second, integrating these techniques specifically in Storm looks promising, because if Modish was dominated by a competitor, it was often outperformed by Storm. From QComp 2020 it is already known that Storm's code base is highly efficient and the performance is currently out of reach for other model checkers on most of the benchmarks. Implementing our approach in Storm would boost its performance even more. To conclude, we introduced a heuristic approach to model check all established property types except long-run averages on general MDP structures. The approach is implemented in Modish. There are several works in the planning community, and contributions to this research line are manifold, but they are quite fragmented with respect to assumptions on property types and model characteristics. We reviewed all of these contributions, gave a full overview of them, and implemented an extended approach with a broader applicability. We reported on a large empirical evaluation that has demonstrated the competitiveness of Modish relative to other state-of-the-art model checking tools. On very large state spaces, our tool outperforms the competitors, demonstrating that planning techniques can indeed be used to enhance the performance and capabilities of model checkers. As a next step, we are looking into performance optimizations like memory and runtime trade-offs. In addition, other heuristics known to work well in the planning community might be worth to implement. Extending the approach to work on other automata types seems also promising. Thank you very much for your attention, and I'm happy to answer your questions now.
Okay, so thank you for that video. So do we have any questions? I see both Holger and Michaela are here. So does anyone have anything that they'd like to ask? So I can start off anyway. Oh no, Arndt?
Arndt has a question.
Yeah, I was just wondering, looking at the evaluation, did you use the, I remember that in QComp we had these two runs of each tool, like one with default settings and one I think with optimized settings. Which one did you use there?
We use the default settings.
Okay. And did you compare with this new dynamic thing in Storm where they auto select their best engine or so? I think I saw Storm static only in your tools, but
right.
You mentioned Storm beats everyone, but I mean that's actually when they use their dynamic selection of engine, right?
Right. So in the paper we only show results for Storm for the static version, not for the dynamic one, but we also tested it with the dynamic version, and I mean, you know the results from QComp already. So even in the static version, Storm is really good, but in the dynamic version, it beats really everyone.
Okay, so even with your extensions to other benchmarks and these large benchmark instances, I mean, Storm still wins on the large benchmarks then with its symbolic engines.
Not on the very large benchmarks. There, Modish wins. Okay. But on most of the QComp benchmarks, which were already in the original QComp benchmark for 2019 and 2020.
I was just wondering when you mentioned that Storm is so optimized, and I think if you take each algorithm by itself, it's not so much more efficient in itself. It has very good implementation of everything, but I think its big strength is that it has this vast amount of algorithms, and if you manage to choose the right one, yeah, then you can't really beat it.
True. So for the very large benchmarks, Modish wins, but for most of the others, or if Modish is beaten by someone, then it's Storm.
Okay, thanks.
So does anyone else have a question that they want to ask? So if not, I'll ask a question. So you say it solves things. So since you're not exploring the whole state space, do you get a precise answer, or is it a bound on the answer?
We have a threshold, and it's often epsilon correct, which means that in most of the cases we really are in between these epsilon bounds we set before, but there can be some MDP structures, like always going back to the initial state, where this epsilon correctness is not managed to get this bound. So this is like usual value iteration and not sound value iteration. So,
but for all of the case studies in QComp, all of the properties have slight thresholds, do they? So that they say, is it true or false? And then you always gave the right answer. Is that?
Yeah.
Okay. Okay, great. Okay, so does anyone else have Arndt's got another question?
Well, trigger if we have time only.
Yeah, we've got time for one more.
I've just been wondering, I mean, I saw PET, which I think is the tool from Munich that uses this variant of BRTDP. In that, how is that, I mean, in terms of the algorithm, how does that relate to your algorithm? Because I mean, it also has RTDP in it, but I think it gives bounds, and I would expect that to be a competitor, but from your plots, it wasn't.
True. So the basic algorithms are similar. It's also labeled real-time dynamic programming inside, and there the abbreviation stems from. But in the end, what they do is quite different from our approach, but the basic algorithms are just the same. But from the plots, you already see that our approach works a little bit better regarding the runtime.
And it's a fundamental difference. It's not just you have a better implementation.
No, no.
Thanks.
Okay, so thanks, Kayla, for a great talk, for great answering questions and for the video. And now can we move on to the next video, which is on tweaking the odds in probabilistic timed automata.
Welcome everyone, my name is Bram Golen and I'm going to talk about our paper Tweaking the Odds in Probabilistic Timed Automata, which is about parameter synthesis. But before we dive deeper into that, I want to look at AODV as an example, which we will use later. So AODV is one of the 4 standardized communication protocols in IETF MANET, and basically what it wants to do is it wants to send messages in a wireless mesh network. So the way it works is there are certain routers like A, B, C right here, etc. And some can communicate with each other like A and B and A and C, and some cannot communicate like A and D. And now we want to send a message. So say that we want to send a message from A to G. So what it does is it sends a message to all of its direct neighbors. In this case, it's B and C, and it tells them to find G. They then send the same message to their neighbors, and they then send the message to their neighbors, etc., until G is found, which we can see here. Now G notices that this message is meant for itself, and it will therefore send a message back. D will do the same, C will do the same, and then we have a path. This protocol was modeled by Kamali et al. Using PTA, and they used PTA because of the probabilistic nature of this protocol as well as the temporal nature. Probabilistic in the sense that if we send a message, the probability that the message is received is usually not 100%. So yeah, there is this probabilistic behavior. And also there's temporal behavior because we want to time out if a message isn't sent within a certain time frame. The thing with PTAs is that probabilities have to be fixed. However, we cannot always be sure that those probabilities are indeed fixed or known. So as an example, we see this wireless mesh network here in the rural part. There are very little buildings, very little nodes. So the probability that a message is received properly is probably relatively high. We see another mesh network here with a lot more nodes, and yeah, those nodes, they can interfere with each other. Also, there are more buildings in the way, there are cars, etc. And this might influence the probability that a message between two nodes is actually delivered. So the probability here is going to be relatively low. So one way to deal with this is to add parameters instead of fixed probabilities and then perform parameter synthesis on those parameters. This is already implemented in Storm for parametric Markov decision processes, in short PMDPs. And yeah, we now want to define a similar notion for the probabilistic timed automaton, which is then the parametric PTA. We then want to convert this parametric PTA or PPTA to a PMDP. And once we have done this, we can actually perform parameter synthesis on that PMDP so that we can perform a valid parameters for the PPTA as well. The last goal is to check whether this approach is actually feasible. So the PTA looks roughly as follows. So this is an example of a simple communication protocol. We didn't visualize AODV because it would be, the model is way too large to visualize on a presentation like this. But yeah, this is also a communication protocol in the sense that we have this clock X, which looks at how long we've taken trying to send the current message, and we have clock y, which takes track of the total time that we have been sending the message. And yeah, we can see if x is greater than or equal to y, the clock x, then we can perform action send, which delivers the message with a probability of 0.9, or the message gets lost with a probability of 0.1. If the message is lost, we don't get an acknowledgement, so we just wait until we are sure that the acknowledgement won't come in anymore, which in our case we chose if x equals 8. So once x equals 8, we know, okay, we have to resend the message. It wasn't received. Clock x is being reset because we are now sending a new message, and we end up here again. So yeah, we have already seen that there are fixed probabilities here and here. But in some cases, yeah, we have seen in the last slide that in some cases this is not the case. So in that case, we want to actually add parameters here in the probabilities. Note that there's also a notion of a PPTA where the parameters are in the constraints. So for example, then there is y greater than or equal or to p here. We are not looking at those kinds of PPTAs. We are looking at the PPTAs purely in the sense of the probability distributions. So yeah, this is a entirely new concept, and we now want to apply parameter synthesis to it. What we want to achieve is that we take a PPTA and the property. We are looking at reachability properties here. So that means that we want to reach a certain state with a probability less than or more than some predefined value. In this case, we want the probability to be greater than 0.91 to eventually reach done, which means that the message is sent correctly. We chose 0.91 because then every value for p greater than 0.7 will satisfy the property, and everything less will reject the property, which we calculated by hand. However, we want to do this algorithmically. So yeah, this is only a reference for what an ideal partitioning would look like. But if we apply parameter space partitioning, then we do the following: we check the entire region and we look if it is consistent. So it is consistent if it is either completely rejecting the property or completely accepting the property. In this case, it is neither, because right here we are rejecting and here we are accepting it. We can find this out through satisfiability checking or parameter lifting. So what we do if it is inconsistent is we split the parameter region. In this case, we split it in half. We can do more other things, but we split it in half for this presentation. And then we do the same for both of these regions. So here we see it is consistent, so we mark it as rejecting because it is. And this is still inconsistent, so we split it again. Now we see that this part here is consistent, and this part is not, so we split it again. Now this part is consistent, and now we actually see that we have covered more than 80% of the entire parameter space. And yeah, we have pre-specified that we want to reach 80% coverage, which means that the algorithm can now terminate. We have to specify this coverage because if we want to go for 100% coverage, then of course you can see that this algorithm will never terminate. It will keep on splitting and splitting and splitting indefinitely. And in most cases, it will never terminate. So we have to specify the coverage. So yeah, that was an example of one parameter. Now, if our model has two parameters, we have a two-dimensional plane. If a model has three parameters, we will get a three-dimensional box, etc., etc. So our question is now, since we have already implemented parameter space partitioning for PMDPs right here, can we also extend this for PPTAs? And we want to do this in a similar way as PTAs are handled for model checking. And that is, we take a PTA and then we use some methods to convert a PTA to an MDP. This MDP can then be solved to obtain a probability. And we want to do the same for the PPTA. So we want to convert it to a PMDP. There are several methods to convert PTAs to MDPs, sorry. So to do this part, we can use, for example, these methods. so digital clocks, backwards reachability, and region graph. And we have actually proven in our paper that this also works for PPTAs to convert into PMDPs. We will look more into these methods in a second, but first of all, we want to mention that these methods also exist, so boundary region graph, but it is not applicable because it is meant for expected reward properties, which we do not consider in this presentation. And also the stochastic games abstraction, which generates stochastic games, as the name says. And yeah, we cannot. It doesn't really fit in this toolchain. Okay, so now we want to look at the methods that we did consider. The first one is digital clocks. So the idea of digital clocks is that we only look at integral time points. So what we do is we start at the initial location, set all clocks to 0, as we can see here. And what we then do is look at what actions we can perform. So we cannot perform action send because x is now 0, which we cannot perform. Y is also 0, so we cannot perform timeout either. So what we do is we let time pass. And because it is digital clocks, we can only let exactly one time unit pass, which sets all clocks to a value of 1. Now we can perform action send. We can also let another time unit pass, as we can see here, but we are not going to consider this branch any further. We are now going to look at what happens if we perform action send. So with probability p, we end up in location done, which we can see here, or with probability 1 minus p, we end up in location lost, as we can see here. In location lost, we have to wait until x reaches a value of 8, which you can see here, and then we can retry, which resets clock x, and we can see here that clock x now has a value of 0. So the reason why this works for parameter space partitioning is because the probabilities here are just directly carried over to the PMDP, and we can now see indeed that this is a PMDP on which we can perform parameter space partitioning. We have proven in our paper in theorem 1 that actually the parameter space partitioning is correct. So another method is backwards reachability, which well, it starts at the target state and wants to go back. So when we are in done, we have here well, we have the state done here, and what we do is we go back through this edge here, and we end up in location init through action send with probability p, as we can see here. We also take the intersection of all of the constraints that we find on the way, which gives us this constraint. We then repeat this, and then so we take this edge backwards, which takes us to location lost. With these constraints, don't worry too much about the details. This algorithm is too complicated to explain in detail in this presentation. And we can then basically redo this until we have found all of the states that are relevant to us. You can see again that this is PMDP, and in theorem 2 we have proven that the parameter space partitioning for this is also correct. So now a quick overview of all the methods. So we didn't really talk about the region graph because it's not really practical for implementation. So backwards reachability and digital clock array are more suitable for implementation. They are still exponential. Backwards reachability is even double exponential, so 2 to the power of 2 to the power of the number of clocks. But in practice, it is still the fastest approach of these three. That's because in practice, we will not even get near to this amount of states. Also, the number of clocks is usually relatively small. For digital clocks, yeah, only a limited set of PPTAs is supported. So, for example, we cannot have strict constraints like x is less than 8, or x is greater than 4. We also cannot compare clocks. So x is less than or equal to y is also not possible for clocks x and y. For backwards reachability, the problem is well, also that for a full implementation we need non-convex zones, which yeah, to look them up is not really that efficient. There's not really a fast way to do so. So that's the algorithmic side of backwards reachability. So next up, we want to look at how to test feasibility. So we use a combination of models and Storm here. Modest we use for the conversion, and Storm we then use for the parameter space partitioning. So what we did is we put the Modest or Johnny files into Modest and parsed them there. Then with digital clocks we obtained a PMDP, which we could convert to a Johnny file and put into Storm to perform parameter space partitioning. For backwards reachability, we first had to do a discrete state space exploration in Modest, and backwards reachability we implemented then as well to be able to obtain a PMDP. We then could export that to Johnny and put that into Storm. So this part here is done by Storm, this part here is done by Modest. What we also had to do is we had to create some new models because there are no parametric PTAs available yet because it is a new concept. So what we did is we took AODV and we took some of the models from the QComp benchmark set. And we then added parameters to them where that made sense. So in BRP and AODV, we added parameters to the probabilities that a message is sent correctly. So AODV, this is the bounded retransmission protocol. Then we have the repudiation protocols with malicious and with honest receiver. So repudiation basically divides a message into multiple packets, and it randomly chooses the amount of packets, and the receiver can only decode them if it has all packets. And we made the probability that each message is the last one, that each packet is the last one, parametric. And for the malicious receiver, we also made the probability to decode the message in time parametric, for which it has two options, and we made both of those parametric. For zeroconf is a protocol that assigns IP addresses, and we made the probability that an IP address is already taken parametric, and the probability that a message is lost is already also made parametric. And for FireWire, we made the probability that we take the fast approach parametric. Then there are also these three models on QComp, which we couldn't really make parametric because they have uniform probability distributions, meaning that all probabilities are the same. So we tested all of these models that are right here, and the results are given in a scatter plot. So this is without actually parameter space partitioning. So yeah, this is not actually new. This is just a comparison of digital clocks and backwards reachability, which we did. And it kind of shows that backwards reachability usually generates a smaller state space, which is good for parameter space partitioning because we have to check a PMDP multiple times. And we can see that a little bit in the results, but we see that there is a small edge towards backwards reachability, as we can see here. So especially if backwards reachability times out, then digital clocks timed out as well, but digital clocks timed out more often, as we can see here. So here we have the same data again, but now in a histogram. And what we can see here is actually another thing that speaks in favor of backwards reachability, which is that because of the backward search, it was able to see that certain parameters were not really important for the probability of the property that we wanted to check. So it was able to completely eliminate one parameter, which basically, since parameters have such an influence on the performance, it was able to do them almost instantly because there was now only one parameter left. We also see that there are here no results for digital clocks, which is caused by the fact that digital clocks doesn't support strict constraints. So what we did was we only tested this for backwards reachability, but we made a version of the repudiation protocols where the strict constraints are replaced by non-strict constraints. So then we could actually check digital clocks on them, and there it was also faster. But we had to actually change the model to achieve this, which is not really preferable. So to sum it all up, we have seen that it is sometimes not sufficient to assume that probabilities are fixed. And we have seen this in, for example, AODV. And therefore, it is important to introduce parameters in these cases. We looked at how to convert PPTAs to PMDPs, which we did through a modest implementation. And then we looked at parameter space partitioning on those PMDPs, which was done using the Storm implementation. And with this, we were able to obtain a parameter space partitioning for PPTAs, which has never been done in the past. And we have also shown that it is feasible to do this using digital clocks and backwards reachability. One side note is that we only check upper bounds, so lower bounds have not really been implemented. There are some issues with divergence and also the non-convex zones in backwards reachability that I've mentioned. But yeah, that is part of future work. So those are the tools that we've used, the Storm and Modest, and yeah, that's about it. We are happy to answer any questions.
Okay. Okay, so I'm trying to put my video on it and I can't. Right, now I can. Okay, so thank you, Bram, for that very nice video. So does anyone have a question that they would like to ask? And it can't be Arndt because he's one of the authors. But if no one else has a question, then we might ask Arndt for a question. So does anyone have anything that they'd like to ask? So first, I can give a comment. So we've extended backwards our reachability to expected time and expected rewards. However, the zones might not have integer values. So we've solved a problem, but I don't think it will help very much with your tool in the size of the models that it can consider. So on to the question. So for the digital clocks results, are you using a symbolic engine?
So for the digital clocks, what we do is we use the so Modest already kind of had this digital clocks conversion. It's only a syntactical conversion. So you only we only look at basically the code of the thing, and we extend it a bit so that it is then an MDP. Okay,
but oh yeah, but it's like parameter synthesis as opposed to verification. So you probably can't use it because for our PTAs, it's like the main gain that you get with the digital clocks, even though it's like the models end up huge, is that they perform well with empty BDDs. Now, I'm not sure how feasible it would be to do parameter synthesis with empty BDDs, but if you could, then it might be the case that digital clocks could actually perform better than backwards reachability on some cases. Okay.
Yeah.
And does that make sense?
Yes. Yeah. Personally, I have not directly worked on the parameter synthesis side of Storm, so I cannot really answer that. But
if I recall correctly, the implementation we were using is an explicit one, isn't it?
Probably. I would have thought so.
Yes, it's explicit.
And a second question: do you have any issues with the size of files that you are generating, because you sort of go from one tool to another? So you obviously have to export these files and then import them again. Yeah. So does that slow things down a lot?
Yeah.
Or
well, slow things down. I think. So we did get some files that were like, I don't know, a couple of hundred thousand lines of code, because especially with backwards reachability, you have to basically export each state separately, or we didn't find any better way. So that would sometimes be quite, yeah, that would be quite large, but Storm actually, well, the output doesn't really take that long, and Storm can actually read them also quite quickly. We did find some problems with reading them to certain other, I think modest certain tools, it has had actually some small problems with that for really large files, but yeah, it's kind of, yeah, it's not for this tool chain. There was not really a problem with it.
I think the point was that the backwards reachability graphs never got so large that we really had a problem. For digital clocks, it's not a problem at all.
Yeah.
The files are the same size as the original one, essentially, but for backwards reachability. And I think for backwards reachability, we're of course using a format that's not made for kind of flat state spaces as we're exporting them. So we could have used a more efficient format than Jani, which is made for compositional models with variables and everything, which we don't have anymore at this point.
Okay, so that's great. So if we don't have any other, last chance for anyone to ask a question. Okay, so let's move on to the final video. So just to thank you again, Bram, for your video. I keep saying thank you for the talk, but it's for the video. And the final video in this our session is on quantifying software reliability via model counting.
Welcome to my talk on quantifying software reliability via model counting. My name is Samuel Teuber, and I did this work together with Alexander Weigel. We are both at KIT in Karlsruhe. Let me first give a brief motivation for our topic. Usually in formal verification, we are interested in whether a certain program is safe or unsafe, or at least that's one important part of formal verification. In this part of formal verification, we want to ensure that some program P corresponds to some specification C. Now, this specification can often be given as assume statements, which constrain the input, and assert statements, which ensure the program behavior. For example, here we have a program where we assume that the input is within some certain input range, and we want to assert that the output, the dividend, is not 0. And that is to ensure that the output is then the correct result of the division. Now, there are some cases where we are not interested in whether the program is safe, but instead we want to estimate the risk. Two examples would be energy systems, where we might be interested in the risk that there is a mismatch of supply and demand. And another example might be prioritizing bugs by their risk. Now, instead of looking at safety, where we want to ensure that the probability that the specification is adhered is 1, we want to measure the reliability, where we want to compute this probability. For example, by computing for how many inputs does P violate or adhere to the specification C. Now let me give an overview on the contribution that we want to present at this conference. First of all, we present a novel and sound formal approach for the assessment of reliability according to adherence or violation of a specification. We do this for both deterministic and non-deterministic programs using model counting techniques, with the objective being that in the end we have a tool where we can enter a program and a specification, and for example we can obtain the number of inputs for which the program fails to adhere to the specification. To this end, based on this formal approach, we implemented a pipeline which processes C programs with assertions and assumptions and allows to quantify those programs using CBMC and model counting. Finally, we evaluated our pipeline on a representative set of benchmarks and did a comparison to Dymowski and Leguet, which presented a paper in 2020 where they presented another approach for the quantification of C programs. Now, what do we mean by quantifying program inputs? Well, first of all, let me mention that we represent programs as tuples of states, where we have a state space large S, and then we have certain states that represent the input and the output, and then the entire program can be represented as a set of tuples of such states. Now we are interested in certain parts of the input space. So we want to partition our input space in the following parts. First, there will be some inputs where we get an assumption miss. That is, the input does not correspond to our assumptions and therefore we dismiss it. Secondly, there may be inputs where the assumption is adhered to. That is, the assumption is valid and we can now look in more detail what is happening for these inputs. And this part of the input space can then be partitioned further. On the one hand, there will be inputs which produce an assertion miss. That is, the input produces program behavior which does not correspond to the given assertions in the specification. On the other hand, there may be programs where we have an assertion hit. That is, the assertions are adhered to and we obtain a successful program run. Now note that in some cases there may be an overlap between the two, which is here marked in red. This is the case if we have non-deterministic behavior within our program, and it can thus be that a program either has a program path leading to success or to failure, both for the same input. Now in this talk we will mostly talk about the deterministic case. The non-deterministic information on this problem can be found in the paper. Now that we have a better image of what we mean by quantifying, let me give an overview on the pipeline that we have implemented. So the first part of the pipeline takes a given program and a specification and transforms this program in such a way that it still has the same start states. However, in the end state, we will then have encoded whether there has been an assume miss, an assert miss, or the specification was adhered to. To this end, we make the specification adherence explicit within the program state and transform our specification in such a way that we introduce special assert statements which later on are checked by CBMC. Now the details of this will be talked about again later. I first want to give a brief overview of the entire pipeline, because the second step of the pipeline then converts CNF into using CBMC. That is, we convert our program into propositional logic formula and conjunctive normal form, CNF. We do this by using the so-called C-bounded model checker, which checks programs with bounded data and execution domain, for example, for violations of assert statements. Now, the formulas produced by CBMC are satisfiable if and only if there is an assert statement violation within the data and execution bound. Now, as I mentioned before, we will introduce special assert statements, which then make it so that the formula is only satisfiable if what we want to count is the case. And finally, in the third step in our pipeline, we then use model counting. And for the model counting, we count the number of models for a given formula. And we project those counts onto the input variables, thus only counting for how many input variables a certain formula is satisfiable. In essence, we basically count counterexamples for some assert statements. Now this model counting will then yield us the four measured quantities that we mentioned above. Now that we have given a brief overview over the entire pipeline, let me reiterate over some important points and also go into more depth on the specific areas of the pipeline. We will begin this discussion by taking a closer look at what CBMC is doing for our pipeline. So as I mentioned, C-bounded model checker is a software-bounded model checker which finds bugs within a given bound. And that bound is both for the data domain as well as for loop unrolls and recursion. They are all bounded up to a certain depth. Now we transform our program into a propositional logic formula. That is, CBMC transforms this program into a propositional logic formula, which basically encodes the entire program flow and what is happening within this program. And now CBMC returns a formula which encodes on the one hand our program, and on the other hand the negation of our specification that we gave in the form of assert and assume statements. Now we need to think about when this formula is satisfiable, because on the one hand it produces it encodes the entire program flow up to the given bound, and on the other hand it contains the specification. This formula is satisfiable if and only if there exists a program path that breaks the specification C. And now by producing one formula per measured quantity, we can then obtain formulae which are satisfiable if and only if the measured quantity is of relevance for this input. Or to be precise, which is satisfiable if and only if we should count this input for our measured quantity. Now let me give an example to make this a bit more precise. We have an example here, again, the same as at the start, where we have an input in a certain range. And now, instead of the condition we had beforehand, we have two options for the condition assert. Now this condition may either be div is not equal to 0. In this case, our CBMC conversion will try to find counterexamples where div is 0. Now in that case, we are able to count the number of inputs for which we might have a bug. On the other hand, we might count with the condition div is equal to 0. And in this case, CBMC finds counterexamples where div is not 0. So it's always the opposite. Now using this formula again, we could then later on, by counting the number of counterexamples, by counting the number of models, we could obtain the number of inputs for which it's impossible that there is an assert violation. Now let me proceed that we have this, now that we have discussed CBMC, let me proceed to discuss a program transformation. The idea of our program transformation, as stated before, is to transform our program in such a way that we still have the start states, however the end states encode whether there has been an assumption miss, an assertion miss, or the specification has been adhered to. Now this is done first of all by introducing global state variables assume miss and assert miss, which will encode whether the program so far has, up to this point in the program, has adhered to both assumes and asserts. Now, next we will introduce a single endpoint for the entire program flow. That is, all parts of the all ends of the program flow will be directed to this one single endpoint using goto statements. And finally, we will then transform our assumptions and assertion misses, assumptions and assertions in such a way that they will set assume miss assert miss, that is, they will set the variable, and they will jump to this endpoint. At the endpoint, we introduce suitable assert statements, which if violated, then produce a satisfiable model, a model for our formula, and that is, they produce an instance which will be counted by the model counters later on. So the first two assert statements that we introduce make it so that we can measure assume hits and assume misses. This is done by always reversing the specification that we actually want to have. That is, in the first case, in our assert statement, we are basically asking that there is not an assume miss, and this way we count assume misses because CBMC puts the negation into the formula that is returned. And we do the same for assertion misses and assertion hits. Note that in this case, we also need to introduce assume miss as a condition because we do not want there to have been an assume miss beforehand. Now let me also give a brief example for this part of the pipeline because I think it will make things more clear. In this example, we're still talking about the input which is constrained and the dividend that isn't supposed to be 0. Now here I omitted some parts of the code, but important things are visible here anyway. First of all, we transform our assume statement in such a way that if the assume is not hit, assume miss is set to true and we jump to end. The same is the case for assert, only this time we go to end and beforehand we set assert miss. Finally, the return statement is transformed in such a way that below the original return statement, we will introduce these assert statements, of which only one will be activated per run of CBMC. That is, we will produce 4 formulae using CBMC, each time with another activated assert statement. Finally, we will then obtain our result, which can then be further used in theory, but in practice, this is basically the end of the CBMC encoding. So now that we have discussed all this, we need to still take a look at the last step of our pipeline, which is the model counting. And for the model counting, we count models for the formula provided by CBMC. And we can do this using off-the-shelf tools like ApproximC or GANAC, which basically allow us to very efficiently count models for propositional logic formula. And that is nice because they're, on the one hand, we can then always get better at our approach every time there are improvements in these off-the-shelf tools. And on the other hand, it's also nice because there are two variants of these tools. On the one hand, we have exact counters, which allow us to exactly count the number of models, but they tend to be not as scalable. And on the other hand, we have tools for approximate model counters, which give you a guarantee on the epsilon interval in which the result will be, and the delta, which is the probability that we will be in this region. And they tend to be a bit more scalable at the cost of being an approximation of the final model count. Now we can use those two, and we can count the projected model counts for the input variables. That is, we count for how many input variables is there a satisfying assignment for our formula provided by CBMC. Now in total, the program transformation, CBMC, and the model counting all together yield us the measurements that we are interested in terms of for how many inputs is there an assert violation, for how many inputs are the assertions adhered to, as well as how many inputs violate the assumption. Now that I gave an overview on the entire and the entire approach, let me talk a bit about the evaluation we did and the benchmarks we used for it. So in essence, we looked at 3 benchmark sets. First of all, we looked at a benchmark set provided by Dymowski and Leguet, which contained simple arithmetic if statements and sometimes very deep loops, and those were 10 deterministic benchmarks. Since those only contained very simple arithmetic and also missed some other, in our opinion, important parts of the C language, we looked at other benchmarks based on the SV competition as well as on the C snippets repository, and obtained some benchmarks which contained bit arithmetic, overflows, small arrays, floats, and we also had an example where we had a look at a larger instance with over 1,000 lines of code to test the scalability of the approach. And those instances build another benchmark set of 9 instances that we looked at. And finally, we also looked at non-deterministic benchmarks, most of them from the previous work, and another one we were interested in using multiplication. Now, for the evaluation, evaluation we're presenting here, we only look at the first 2 benchmark sets, simply due to time constraints. However, there's more information on the 3rd benchmark set in the paper. Now, let me start with the results on our first benchmark set, which are the benchmarks previously used by Dymowski and Leguet. And here we notice that the functions are, as I mentioned, only contain very basic arithmetic operations and sometimes very deep loops. For example, in this case, there will be multiple hundreds of loop iterations necessary for this case. And this is very easily analyzed for abstract interpretation because there's no need for an unroll. So these benchmarks in this benchmark set are very well suited for abstract interpretation. However, they are not so well suited for bounded model checking. And so it's clear to say that we cannot compete on this original benchmark set by Dymowski and Leguet with our approach simply because of these loop unrolls. However, we noted that these benchmarks, there's a number of things they don't contain, in particular bit arithmetic, floats, arrays, as well as large instances. So we tried to form a small benchmark set containing some of these properties and try to find representative examples. One of those is a square root algorithm, which computes the square root. And this is a modified example from the C snippets repository. And we have a problem here because at the computation of lower, we have an issue as there is an arithmetic instead of a logical right shift. Now, this is problematic because if the numbers are high enough, this might produce errors. And we can actually analyze this example very well with our pipeline. So for our transformation, we take about 1.5 seconds. And with approximC, we can count the counts within some 17 seconds. And we then obtain that for 2 to the power of 31 cases, the assumption is missed. So for all negative numbers, that is already very, seems to make sense. And then for 2 to the power of 30 cases, we have a bug. And that is simply if the second highest bit is set in this case. So now that I gave 2 examples from our evaluation, I will just give a brief summary of what our evaluation shows. First of all, loop depth is the most influential factor. That is, if loop depth is too high, our approach tends to show worse results. I think that's very intuitive. CounterSharp supports a larger share of C programs in comparison to Dimowski and Leguet. The largest instance we were able to solve contained 1.3 thousand lines of code, and it took some 725 seconds with approximC. And note that Dimowski and Leguet were not able to analyze this instance. It seems that they simply ran into a timeout. And the bit-precise semantic helps sometimes. So there are cases where our approach will be more precise, as it can, for example, detect overflows. Now let me conclude with reiterating on the contribution. We presented a sound formal approach for the quantification on the soundness. There's also some notes in the paper on this. We then built this quantification pipeline for C programs to check their reliability. We also, in our paper, present some error bounds for the reliability measurement for approximate counting, since you need to take this approximation into account. And we also did an evaluation and compared 3 benchmark sets. Now for future work, we are interested in counting beyond uniform input distributions, since usually one might assume that there's some non-uniform input distribution on the input that is given to the program. To that end, one might be interested in projected weighted model counting. It would also be interesting to adopt this approach to other languages, and one could also think about ways to improve the scalability of the approach. Now, I'm very thankful for your attention, and I'm looking forward to your questions. Thank you.
Okay, so thanks for the our presentation. So we have Samuel, I think, is here to answer a slight question. So we have a question from, or 2 questions from Enrico, but I think that you just answered the first of these. So this asks, the final measure of the risk should in principle depend on the prior distribution of inputs, and are you assuming that it's uniform? And can you confirm that you said that in the last slide?
Exactly. So far, we assume it to be uniform. However, there are weighted model counters, and one would still have to look at how one can do projected weighted model counting in that sense, but that should certainly be possible as well. And so that would be the answer. That's future work. Yep.
And our second one is, once you've identified the counter examples, why cannot these be removed? Is this about using a faulty implementation that cannot be patched?
Exactly. So one scenario would be where you have an implementation where for some reason it's impossible or very difficult to patch a certain bug, and before investing that effort, you might want to find out how relevant it is. I mean, that obviously all depends on the scenario where you are using this software. And another one would, as I mentioned in the introduction, another use case might also be if you have multiple bugs that you need to have fixed, and you might be interested in looking at which bugs have a higher risk on the reliability of the software.
Okay, so thank you. So does anyone else have any questions? And Enrico said thank you, so I think you've answered his questions. So does anyone else have a question that they would like to ask? Okay, well, in that case, I'd like to thank you again, and I'll bring this session to a close, which is only a few minutes over. So there's now a break until 1:45, and then there'll be a